Hello, guys. So, welcome to chapter 7. Chapter 7 talks more about how can we harvest energy. So, we spoke a lot about generally the thermodynamics, the changes of energy, how we're able basically to take up energy and how we can transfer it, and the laws, the laws within this that, we cannot create, we cannot destroy energy, first law of thermodynamics, and we can only transfer it. Great. But then when we transfer it, it's not 100%, meaning that when we transfer energy, some of it is going to be lost, and that's basically entropy. And that is the second law of thermodynamics. So now we've learned more the mechanics of how energy is you know given and how it's transferred and all that. And we also spoke a lot about enzymes and how enzymes actually help us carry out all of these energy transfers. So now in chapter 7, we're going to use that information that we took from chapter 6, and now we're going to actually start to really see how, can we get energy from outside and how we can we transfer it to us to give us energy. So now we know basically a bit the laws of it. So now let's apply it properly. How do we get, for example, us humans get energy from food? How do we start from chewing something and then converting it into, let's say, ATP? How does that happen? So all of us have to have something called cellular expiration. And cellular respiration literally is the extraction of energy from organic molecules. In other words, what we do is that we oxidize organic molecules to extract their energy and basically transfer it to us. That's cellular respiration. So remember oxidation. So remember this from redox reactions. Oxidation is basically when you remove electrons. That's what oxidation means, is that when you get an organic molecule, we keep removing its electrons in order to take its energy. Because when you remove the electrons, you're removing the energy. So that's one thing we're doing. We're trying to remove this energy from those organic molecules and we're trying to transfer them to us. So that's literally cellular respiration. And in Earth, there's two types of organisms and how they're able to actually, acquire this energy. You have autotrophs and you have heterotrophs. Autotrophs are more like animals or bacteria that are able to do photosynthesis. These guys are able to actually create their own organic molecule. So they take the energy from the sun, they transfer it to them, and they create the organic molecule. Once they create that organic molecule, then they'll basically be able to break it down or oxidize it to get energy from it. So those are autotrophs. Heterotrophs are basically organisms that cannot do that. We cannot create our own organic molecules. Just like us, we cannot create organic molecules from the sun. We basically get it from other organisms. Us humans, we cannot just go to the sun and then be like, okay, body, start creating glucose. That's not gonna happen. You get glucose by eating. So that's a heterotroph. You live on organic compounds produced by other organisms. So those are the differences. Autotrophs being they're able to create organic molecules. Heterotrophs are basically organisms that live off on organic molecule compounds produced by other organisms. So now let's go into cellular respiration a bit more. So as I was saying, cellular respiration is literally the oxidation of organic molecules. We oxidize them to remove electrons and transfer this energy. Because of course, when you remove electrons, you're removing energy. Because basically, to remove an electron, you need energy. Basically, energy is going to be released. So you know that's how basically we are able to take the energy. So when you remove electrons, these electrons still have energy in them. We don't want to lose them. So what the best thing for us to do is actually, accept them, have some sort of molecule coming in and accepting these electrons. So we can still maintain that energy. So we basically have some compounds that will gain an electron. And this is again the redox reactions. So when we break down these um, organic molecules, so we oxidize them, they're going to lose electrons. We don't want to lose those electrons because they still have energy. So we actually have other compounds that will gain them. And that's reduction. So they're becoming reduced. So when these things happen together, these are called redox reactions. And actually, cellular respiration is actually multiple redox reactions, which we will definitely go into a lot of details, uh, right, actually, here in this chapter. So in this case here, it's not just actually the loss and gain of electrons. There's something called dehydrogenation. So here, the loss of electrons that we're basically, when we break down this organic molecule, sure, we're breaking it down and releasing electrons, but you also lose protons and basically the form of hydrogen. So basically, when you lose hydrogen atom, you lose an electron and one proton because hydrogen atoms have one electron and one proton. They don't have any neutrons. Remember that. So when we oxidize, when we basically kind of get this, um, organic molecule and we oxidize it, we actually dehydrogenate it, meaning that we remove its hydrogens, which have this one electron and one proton. So this is what happens here when you oxidize it. And of course, the reduced agent is going to gain an electron, but also a proton as well. So as I was saying, you basically, of course, you have organic molecules that are losing electrons. And as we said, because we don't want to lose that energy, we want a molecule that's going to come and accept that electron. So to still conserve that energy. And though basically we need a reducing molecule. In this case, we actually have a lot of them in our body. And one specific one is this nicotinamide adenosine dinucleotide, this NAD plus. NAD plus is basically, it has a positive charge. It loves to accept two electrons and one proton to become NADH. And when it becomes NADH, NADH by itself can then also lose, those two electrons and proton to again give you NAD plus. So one thing you see about NAD plus, it keeps changing from NADH to NAD plus. So in our body, we have a pool of NAD plus and a pool of NADH. And that pool has to be quite equal because we need, NAD plus to always, to be acceptors. We need them to accept. So we need a big pool of this. So when these they go to NADH, they need to go back because if we lose all our NAD plus, we don't have a lot then of kind of these acceptors, these reducing compounds that are able to accept electrons. So we will be losing those electrons if we lose NAD plus. So that's why this has to be reversible. So let's give you an example of how NAD plus, is able to take. So let's imagine you have a energy-rich molecule. So this molecule, we're trying to oxidize it to take its energy. So basically, it's going to come and bind to the enzyme. Once it binds to the enzyme, NAD plus is going to then also be able to bind. So NADB plus is going to be a cofactor of this whole enzyme because it's going to help the enzyme actually do the catalysis. So basically, the catalysis here, as you see, you basically have two electrons and a hydrogen proton being transferred to NAD. So then NAD, basically here now you have an electron giving you NAD neutral, and then you're giving another electron to it, so it's going to be NAD negative, which is then going to be balanced out by giving a hydrogen. So in total, you're going to get an NADH. So that's basically then its final reduced form because now it basically gained electrons, and this high energy rich molecule is oxidized because it lost electrons. So now this product is gone with an H plus that we don't need, and then you have the NADH. So that's how this NADH is able to, receive these electrons. Because then these electrons that basically it has, it can still use them to create energy. And we'll talk a lot about that. So that's a very important because now when we get this high energy rich molecule, when we oxidize it, sure, we break these bonds, a lot of energy is released and we are able to use that energy. But of course, electrons are going to be, because we broke the bonds, electrons are going to escape, and we need to catch them because those still have energy that we still like to conserve. So that's why NAD is there to be able to catch them and then basically later on use those electrons. So what we're trying to do is be as efficient as possible. So we get this energy-rich molecule. We already take the energy from breaking these bonds, these hydrogen bonds. Basically, we break them, we take the energy, but the electrons that are basically taken out, we take them because these still have been energy. We can squeeze that out a bit more. So think about this as literally you have a lemon and you're trying to squeeze every single juice out of it. Well, that's exactly what we're trying to do with this energy-rich molecule. We're taking the energy from breaking the bonds, and we're also then taking the energy from the electrons being released. So we're squeezing every single, juice of energy from this energy rich molecule. That's what we're trying to do. So as we said, basically, and when it comes to cellular energy harvest, so cellular respiration, there's dozens of redox reactions taking place. And what we're trying to do is we get um, this high energy rich molecule like glucose. And what we're trying to do is we're trying to keep oxidizing it and try to remove all of its energy as much as we can. And the more we break the bonds, the more electrons are going to release. So a lot of energy, we need to have NAD always there to trap the electrons because we can use those electrons later on. And then this NAD plus, basically when the NAD plus takes NADH, NADH will basically have these electrons, and they need to basically then pass the electrons to something else, to the final electron acceptor. And when they pass it to final electron acceptor, this actually helps in creating energy. And we'll be talking a lot about that. So as we said, let's go back here. When you create NADH, it will basically now have a lot of basically it will have electrons, and these electrons have energy. So the best thing for that is to pass it on to basically a final acceptor. So we call this a final electron acceptor. And when it passes it to the final electron acceptor, this creates energy. It's passing it, and we'll be talking about that a bit later. But what is that final acceptor? Well, it can be basically either oxygen or something else. If the final electron acceptor is oxygen, it's called aerobic respiration. Aerobic means that there's oxygen. If there's no oxygen, so anaerobic, the final electron acceptor is an inorganic molecule. This is anaerobic. If basically there's no oxygen and you go for inorganic molecules. If it's organic, it's fermentation. So what you're doing here is that, of course, when we uh, destroy this energy-rich or we oxidize this energy-rich molecule, we are creating NADH, from a redox reaction. This NADH now has these extra electrons that it gained, and we want to pass it on to a final electron acceptor, because by passing it on, you're creating energy. How? We'll speak about that later, but just focus on that. We need to basically pass on these electrons. Where are they passed on the final acceptor? Tells you what respiration it is. If it's oxygen, aerobic. If it's inorganic, anaerobic. And if it's basically a organic molecule, fermentation. Now we'll be talking a lot about them, specifically aerobic and fermentation. So when we talk about aerobic respiration, which is actually the main type of respiration that we have in our cells, we basically what we're trying to do is we're trying to break down a energy rich molecule. That's what we're trying to do, and basically have oxygen as your final electron receptor, basically receptor. So this is that's basically this should be acceptor. So this is the final acceptor. That's the aerobic respiration. And this high energy molecule is glucose. We spoke about this. Glucose is the basically this subunit that helps us actually create energy. And as we said, we need oxygen. So imagine that you have basically one glucose molecule, shown here, and then you have oxygen. And what you're going to do with this is with this, because it's aerobic, so there's oxygen, you're trying to break down completely or oxidize this glucose into six CO2 molecules, six water, and energy, which is either coming in heat, but also in ATP. So in general, if you get glucose right now, and you basically, for example, put it in oxygen and you burn it, you're going to release minus 686 kilocalories per mole of glucose. That's the standard if you just do that in the lab. If you do this in a cell, you get even more. You get 735, if I'm not mistaken, kilocalories per mole. So you get more free energy from if you do it in a cell. But why? Why is that? Well, it's simply because when you do this in the lab, what you're going to do is that this is one reaction, and basically what you're going to do is you're going to actually completely destroy this glucose directly in one step. And when you do that, you're releasing so much energy that a lot of it is going to be lost. So when you actually break a lot of energy, some of that is going to be lost. But it's more efficient if you do it step by step, because if you do it step by step, the breaking, you actually minimize the loss of energy. That's one thing. Two is that if you also break this in one go, So much energy can be released, but also a lot of heat. And this can be very combustible. So that's why the body doesn't want to do that. And the same thing in the car. When you go burn um, your fuel, you don't burn it all together. You do it bit by bit. Because if you burn it all together, you release so much heat that it actually can burn down the whole car. So you burn it bit by bit, releasing bits of energy that are then can be basically used um, to push the car forward and minimize the amount of basically heat being released, this kind of energy that we cannot use. So that's why when it comes to a cell, we break down glucose into smaller, basically in small steps, not in one go. So that's why the free energy, the total energy we can use, is much more in the cell than basically if we do this in a standard condition and where you have one reaction. So you have to remember. So this is basically electrons that are coming from food. If we go from here straight to here without the steps, like in one go, a lot of energy is going to be released because again, if you're basically electrons being transferred from one place to the other, it's basically every time this electron is being transferred, it loses energy. Remember, transfer is not efficient, so always you have energy being lost a bit. So that's why it's going, if it when it comes to here, it's losing energy. So from it goes from high energy to low. So if basically this electron goes straight away without the steps, it's going to lose a lot of energy, and that energy could be released as a lot of heat. So that's not the best thing you want to do because that is very combustible. So the best thing is to actually let it go by step by step. So as you can see here, that's so very minimal. So if from here to here you lose a bit of energy and a tiny bit goes basically as heat. Then here the same thing, a bit goes as heat, here a bit of heat, but the amount of heat that goes in the steps is much lower compared if the electron went from here to here straight away. So that's why it's very important. And this is why we need NAD. Because NAD is gonna basically come here and accept these electrons. And then basically the NAD is gonna come down and it's gonna give it to oxygen, in this case of aerobic. So it's gonna give you the steps rather than basically going through this equation. Like you directly take glucose, you break it down and you skip the steps and you go do one massive step. Well, the impact is gonna be much higher. You lose a lot of energy and a lot of it's gonna go from heat. So it's not that efficient. So as we said, from here to go to here to this step, you need electron carriers. So basically the NAD. So these are the guys, the reducing compounds, the ones that are going to be reducing. And these are called electron carriers. And one of them that we know is NAD, this nicotinamide adenine dehydrogenase. So NAD, it has the following actually structure. So this is NAD plus, so the oxidized form. It actually is made of two nucleotides. So this is the first nucleotide. This is the adenine nucleotide. If you guys remember, this is adenomonophosphate. This is the adenine. This is the ribose sugar, and this is the phosphate. So this is adenosine monophosphate (AMP), and it's then basically this phosphate is then bound to another nucleotide that has this nicotinamide. So all the action, all the basically acceptable electrons happens in this one, in the nicotinamide nucleotide. Not here in the adenine, this area is more actually responsible for binding to enzymes, but this is more doing the job. This is the ones accepting electrons. So when it accepts electrons, so it might basically focus mostly here. Look what happens. So basically you have the acceptance of in H, and you also get basically electrons coming in here and also here. So you get two electrons and a hydrogen proton. So then it gives you NADH. This is the reduced form of the nicotinamide. So when we have electrons from food, NAD plus is going to come here. It's going to accept these two electrons, and then basically it's going to go down the steps, and then it's going to be passed down to oxygen as the final acceptor. This is very important to keep in mind. So at the end, the principle of all of this is when you break down or oxidize compounds, or basically these organic molecules, what you're trying to do is by basically create ATP. Because as we know, ATP is literally the unit of energy. It's like, the currency. because we need ATP to fuel endergonic reactions because we know that ATP has a lot of energy stored in the phosphate bonds. So if we break one of those bonds from ATP, we get around 7 - 7.3 kilocalories per mole of free energy. And that can help us a lot to drive endergonic reactions. So this whole thing of breaking this energy rich molecule is to basically the energy released here is going to help us drive ATP production. But also the NADH, when it accepts electrons and it's passing the electrons through, its main goal is also later on to create ATP. So ATP can be created two ways. The first way is the substrate level phosphorylation. And this mostly happens when we actually break down glucose. And when we break down glucose, the energy released, we use it to power phosphorylation of ADP. So ADP is basically adenine diphosphate. So when we basically break down glucose, we have energy, and that energy is going to help a phosphate come here and become ATP. So here's an example. So you have basically this phosphoenol pyruvate, this PEP, which has this high energy phosphate. So here you have adenyl diphosphate, so adenine diphosphate. So when we break this bond, this is actually comes from glucose. When you broken down glucose into this, when we break then this, what we do is we break this bond and we transfer this bond here to the phosphate, so creating ATP. So by breaking this, we've supplied the energy to come down to basically be transferred here. So this is basically one way, which is called substrate level phosphorylation. And this happens through glycolysis, which we'll be talking about. And the second is this oxidative phosphorylation. And this uses basically this ATP synthase, which is a enzyme that creates ATP, hence the name ATP synthase. It creates ATP, and how does it create an ATP? Is from this high energy electrons that are being passed around from the NADH to other carriers that we're talking about. And we'll go definitely into details. So again, you have the substrate what's it called? The substrate level phosphorylation, and this comes from the breaking of these bonds. Because when you break these bonds, when you break this energy-rich molecule, you give energy, and that energy is gonna then help ADP be basically phosphorylated, so given an extra phosphate to give you ATP. And then when you get this NADH, that's gonna fuel your oxidative phosphorylation, and it's going to fuel your ATP synthase, which is going to help it actually create more ATPs. We're going to definitely go into much more details about this and that. But what I want you to here keep in mind is how electrons are being that basically that when we break energy-rich molecules, the energy that's released, we use it to power actually ATP production. But also the electrons that are removed, we need them because they can actually we can use them to even further push ATP production, and hence we need these kind of electron carriers, the ones that are going to accept them. So NAD here in this oxidized form is going to come and it's going to accept it and it's going to become reduced. So this guy's going to have a lot of electrons, which is going to then fuel it to the ATP synthase to create more ATP. And actually, you create more ATP through here, then basically then supplying just a bit of energy. So that's what we're going to go next into, which is basically the oxidation of glucose that we're going to be explaining in part 2.